Welcome to Science to Sleep By. Tonight, we drift into a story carried on the quiet breath of the earth itself. A story shaped not by myth or imagination, but by the patient instruments that watch our skies, our oceans, and the restless edges of our planet. From the coastlines of Maine to the desert plains of Arizona, from the snow-brushed peaks of the Rockies to the quiet neighborhoods of the Midwest. Preparing for another winter, the United States sits beneath an atmosphere that is never still, never silent, and never entirely predictable. And now, as December 2025 approaches, NOAA, the National Oceanic and Atmospheric Administration, has released a forecast unlike any they have issued in recent years. Not a warning meant to frighten, but a signal, a scientific whisper, that the atmosphere is building toward something unusual. Tonight, in this gentle, Science to Sleep By journey, we'll explore what NOAA has seen, why their December 2025 projection has stirred the scientific world, and what it could mean for winter across the United States. So settle in. Let the details drift over you like falling snow, and let the science guide your imagination, slowly, softly, toward understanding in the quiet months leading into the winter of 2025. When most people in the United States were turning their attention to holiday plans, evening lights, and the familiar rhythm of cooling air, a very different kind of focus was unfolding inside NOAA's vast network of laboratories and observation centers. While the world moved normally, NOAA's instruments were whispering a different story, one that didn't shout or scream for attention, but instead pressed gently, persistently, like a quiet hand tapping a shoulder. It began with subtle fluctuations in wind speed at high altitudes, the kind that meteorologists observe carefully, but usually file under natural atmospheric variability. Yet in late September, those fluctuations became less random, more patterned, almost as if atmospheric currents that normally danced freely across the northern hemisphere had begun hesitating, pausing, and then bending in unusual ways. To the scientists watching, it was not a moment of panic, but a moment of deepening curiosity. NOAA's satellite arrays, orbiting far above the curved horizon, were detecting temperature gradients in the upper troposphere that did not fit the typical early winter signatures. Normally, as autumn yields to December, the temperature difference between the equator and the poles increases sharply, tightening the jet stream and drawing energy across the continent in a predictable sweep. But this year, the difference was uneven, as if the atmosphere were holding conflicting signals. Some regions above the Arctic were warming more rapidly than models projected, while pockets of the Pacific atmosphere were cooling abruptly, creating a thermal tug-of-war that scientists had not seen with this intensity in almost 2 decades. As NOAA ran more simulations, they noticed that these temperature disturbances weren't isolated. They were part of a larger atmospheric reconfiguration that began months earlier in the Pacific Basin. Deep beneath the surface of the ocean, near regions where warm and cold currents twist around each other like strands of a braided rope, sensors detected a pulse of heat rising upward. This kind of subsurface warming wasn't dramatic enough to trigger global headlines, but it was precise enough to modify how moisture evaporated into the air above the ocean. Even a small change in ocean-atmosphere coupling can ripple across the hemispheric climate system, and by October, the ripple had become a wave. That wave collided with another pattern NOAA had been tracking more quietly, a weakening of the stratospheric polar vortex. The polar vortex is like a massive spinning crown of cold air anchored over the Arctic, and when it becomes unstable, winter across the United States can take strange, unpredictable paths. But this year, the vortex's instability was not gradual. It wavered suddenly, destabilizing earlier than expected. Instruments detected a thinning of its outer ring, a sign that warm air was intruding from lower latitudes, pushing against the cold walls that normally shield North America from early-season atmospheric disruptions. Individually, none of these anomalies would have prompted an urgent bulletin, but together, they created a mosaic of atmospheric behavior that did not match NOAA's long-term projections. The atmosphere was shifting, its architecture, recalculating the rules that winter usually follows. NOAA scientists double-checked their findings, comparing them to decades of archived data stretching back through El Niño cycles, volcanic eruptions, and solar minima. Nothing aligned perfectly. The closest precedents came from rare years when multiple atmospheric systems fell out of phase with one another, leading to winters that were remembered not for destruction, but for unpredictability. By early November, the internal discussions at NOAA grew more focused. Data analysts, climate physicists, and seasonal forecasters gathered in conference rooms lined with glowing maps, each map displaying color-coded swirls representing wind patterns, pressure anomalies, and moisture flows across the Atlantic, Pacific, and Arctic regions. The conversations were calm, methodical, but edged with a kind of scientific fascination. They knew that December 2025 would not be a typical winter onset. They knew this shift was not simply a cold spell, nor a warm spell, nor a storm-heavy pattern. It was something else, something more nuanced, something that required a new way of interpreting the atmosphere's evolving signals. When NOAA finally prepared the bulletin, they crafted it carefully, choosing words that expressed the seriousness of the observation without crossing into alarm. They explained that December-May 2025 bring unusual atmospheric behavior across the United States, driven by a convergence of oceanic warming pulses, jet stream irregularities, and early-season polar vortex disruption. They highlighted that forecasting confidence was unusually high, not because models agreed in detail, but because they agreed that the atmosphere was entering a period of heightened volatility, not chaotic volatility, but structured volatility, the kind that indicates the climate system is reorganizing itself on both short and long timescales. Behind the public bulletin was another layer of insight, one that NOAA shared mainly within the scientific community. They saw evidence that Earth's atmospheric engine was responding more quickly than projected to oceanic temperature anomalies. They noticed that the Pacific Basin, a region that governs much of the Northern Hemisphere's winter behavior, was sending signals that didn't match the typical patterns of El Niño or La Niña years. Instead, it resembled a blend of both states, a transitional phase where the ocean was neither warming nor cooling steadily, but oscillating in pulses. These pulses interfered with the atmospheric wave trains that guide storm tracks across North America. In some simulations, storm tracks dipped sharply south, grazing the Gulf states. In others, they remained locked in the north, dropping intense snow over the upper Midwest. This variability made December particularly difficult to forecast with precision, yet it reinforced one central conclusion: something fundamental in the atmosphere was shifting. And NOAA's role was to translate that shift into meaningful information for the public. Across the country, most people never sensed that anything unusual was happening far above them. They went to work, prepared for the holidays, and enjoyed the routines that winter brings. But high above the United States, in the quiet swirl of cold air mixing with unexpectedly warm currents, the atmosphere was writing a different December than the one people expected. And in NOAA's bulletin, written with scientific clarity and shaped by thousands of data points, the message was clear enough for anyone listening closely. The winter ahead was preparing to bend the familiar pattern in ways the nation had not seen in many years, far beneath the surface of the world's oceans. In the quiet blue darkness where sunlight can no longer reach, Earth stores an enormous amount of energy. It is a place that feels still, but is never truly still. Water moves in slow, deep rivers, pushing warmth and salt and nutrients across entire hemispheres. In the months leading toward December 2025, NOAA scientists noticed something in this deep, slow-moving engine of the planet. A subtle, but persistent, signal rising upward from the Pacific Basin. It wasn't dramatic enough to generate immediate headlines, and it didn't resemble the classic patterns that define a strong El Niño or a strong La Niña. Instead, it appeared as a pulse, almost like the steady but unmistakable heartbeat of the ocean shifting rhythm. This pulse was detected by NOAA's network of Argo floats, drifting instruments that measure ocean temperature and salinity from the surface all the way down to great depths. Normally, these floats record gentle seasonal cycles, or the long, wavering signature of climate oscillations. But throughout mid-2005, several clusters of floats began reporting a consistent warming at depths of several hundred meters. What made this event unusual was the timing. Subsurface warming typically builds earlier in the year, but this pattern intensified as the northern hemisphere was approaching winter, a period when the ocean should be gradually releasing heat, not accumulating it. NOAA's oceanographers spent weeks cross-checking the data, comparing it to historic records and climate model outputs. They discovered that the warming pulse aligned with subtle shifts in the thermocline, the boundary layer that separates warm surface waters from colder, deeper waters. In the eastern and central Pacific, the thermocline had begun to tilt more sharply than expected, lifting warm water upward while pushing cooler water downward in ways that disrupted normal heat distribution. This vertical motion didn't just change the temperature, it changed the behavior of the ocean-atmosphere interface itself. As warm water rose closer to the surface, evaporation increased. But it wasn't the kind of evaporation that feeds massive tropical storms in the summer months. Instead, it was a slow, persistent increase in atmospheric moisture, the kind that can quietly intensify winter storms thousands of miles away. Moisture is the silent architect of winter weather. Even a small increase in available water vapor can dramatically enhance snowfall totals, strengthen coastal storm systems, and shift the boundaries of freezing and thawing. NOAA scientists knew that if this warming pulse sustained itself into December, it could create winter storms with unusually high moisture loads, especially when interacting with colder continental air. What made this situation even more intriguing was that the warming pulse wasn't uniform across the Pacific. There were pockets of intense heat surrounded by cooler zones, like warm islands set inside a sea of colder currents. This patchiness disrupted atmospheric wave trains, patterns of energy that ripple across the Earth's atmosphere and influence the placement of high and low pressure systems. These wave trains act like the steering wheel of the atmosphere, guiding storm tracks across the United States. When they shift unpredictably, storms that usually follow a northern path can swing south, and systems expected to remain offshore can curve inland. By late October 2025, NOAA's Seasonal Forecasting Division began conducting scenario simulations using supercomputers that modeled thousands of possible winter outcomes. While the details varied, one signal remained consistent: the warming pulse created a higher likelihood of atmospheric instability. Storms were more likely to reorganize rapidly, changing intensity or direction over short periods of time. Across much of the United States, this meant winter weather that could feel sharper, wetter, and more dynamic than typical early season patterns. Another layer of complexity came from the atmosphere's response to this oceanic warming. As moisture increased over the Pacific, high-altitude wind patterns began to shift. Jet stream segments strengthened in some areas while weakening in others, creating pressure gradients that pushed weather systems into unfamiliar positions. This kind of jet stream distortion is often associated with significant winter anomalies. It can bring unusual warmth to some regions and sudden cold snaps to others. But in this case, the distortion suggested something more subtle: frequent oscillations between warm and cold periods, producing rapid freeze-thaw cycles across large portions of the United States. NOAA scientists were particularly focused on this freeze-thaw behavior because it has far-reaching impacts. Roads can deteriorate faster, agriculture experiences stress, and energy demand becomes harder to predict. Snow falling on warm ground melts quickly, but when temperatures suddenly drop again, that moisture can turn to ice. The ocean's warming pulse, though far away from the continental United States, was quietly setting the stage for a winter that might feel inconsistent and unstable, even if the individual storms were not extreme. In addition to the direct atmospheric effects, NOAA's climate researchers explored deeper implications. Subsurface ocean warming can indicate that heat absorbed by the ocean in previous seasons is beginning to return to the atmosphere. This kind of delayed release can intensify long-term climate patterns and produce months of atmospheric behavior that feel disconnected from more immediate weather events. It suggested that December 2025 might not simply be reacting to short-term conditions, but responding to energy that the ocean had stored years earlier. As NOAA synthesized all this information, one theme emerged: the ocean was speaking more loudly than usual. Its warming pulse was subtle enough that the average person walking along a beach or scanning a weather app would never notice, yet powerful enough to shift the behavior of an entire hemisphere's winter. It created a sense of complexity, a layered interplay between deep ocean currents, atmospheric moisture, heat transfer, and global wind patterns. December 2025 was shaping up not as a winter defined by one dominant force, but as a season sculpted by many small forces moving in harmony and tension at the same time. Scientists at NOAA approached this moment with a mixture of caution and fascination. They knew they were witnessing a rare type of ocean-atmosphere interaction, the kind that challenges long-standing assumptions and offers new insights into how Earth's climate machine operates during transitional periods. They analyzed satellite imagery, buoy data, and climate indices day after day, watching the warming pulse rise, spread, and intertwine with atmospheric systems above it. And although their projections for December carried uncertainty in the details, the overall message remained unmistakable. The ocean was preparing to influence the winter ahead in ways that were both intricate and deeply connected to the hidden warmth rising within its depths shy above the surface of the Earth. Far beyond the rooftops, mountains, and the drifting quiet of early winter clouds, the atmosphere holds a river of wind that never appears on any map. It does not shimmer like water, and it makes no sound you can hear, but it moves with a speed and force powerful enough to shape entire seasons. This river is the jet stream, a narrow band of air that circles the northern hemisphere, guiding storms, carrying temperature fronts, and dictating how winter settles across the United States. In most years, it flows as a broad but unified current, steady enough that meteorologists can predict its general behavior weeks in advance. But as NOAA reviewed the atmospheric data leading into December 2025, they saw something forming that changed not simply the strength of the jet stream, but its very structure. Instead of one cohesive current, the jet stream began developing a pronounced split. It was as if the atmospheric river had forked into two separate channels, each trying to carve its own path across the continent. This split is not unheard of, but the timing and magnitude of the division stirred quiet discussions within forecasting rooms. When the jet stream divides, it creates what some meteorologists call a winter divide, a season where regions of the United States may experience drastically different conditions at the same time. Warmth can surge unusually far north, while bitter cold plunges unexpectedly south, all because the atmosphere's steering current is no longer unified in purpose. NOAA scientists first noticed the weakening in the jet stream's core flow during early autumn. They observed subtle fluctuations in wind speed at high altitudes, irregularities that might pass without concern in a typical year. But as October turned to November, these fluctuations intensified. Wind velocities dropped in some sectors while accelerating sharply in others, creating tension along the stream's edges. That tension is often a precursor to atmospheric deformation, the type that causes the jet stream to buckle, twist, and eventually split. The driving force behind this shift appeared once again to be the complex blend of warm and cool air masses forming over the Pacific and Arctic regions. The deep ocean warming pulse, the uneven atmospheric temperature gradients, and the polar vortex instability all contributed energy into the jet stream's architecture. As the polar vortex wavered earlier than expected, cold air that is usually trapped at high latitudes began interacting with milder air from the mid-latitudes. This interaction pushed downward on parts of the jet stream, forcing its southern segment to dip more sharply over the central United States. Meanwhile, a separate branch of the current curved northward, sweeping warm Pacific air into regions that would normally be preparing for early snowfall. The result was a split pattern that stretched across the continent like a loose seam, separating two different atmospheres. Meteorologists describe such a split as the creation of two storm highways. The northern branch guides systems across the northern tier of states, often bringing warmer temperatures and mixed precipitation. The southern branch becomes a corridor where colder, denser air interacts with moisture from the Gulf of Mexico and the Pacific, amplifying the potential for significant winter weather events. When these two branches run parallel, winter becomes divided not by latitude alone, but by the invisible structure of wind itself. NOAA analysts spent hours comparing this projected split to historical winters, searching for analog years. A few came close, but none matched the exact configuration developing in late 2025. The models showed that the southern branch of the jet stream could become unusually active, dipping farther south and then slingshotting eastward toward the Atlantic coastline. This kind of pattern often leads to frequent storm formation along the Gulf states, the Tennessee Valley, and up through the Mid-Atlantic corridor. Moisture entering the southern branch is lifted and intensified, sometimes producing deeper low-pressure systems capable of bringing heavy snow, freezing rain, or strong coastal storms. For residents of states like Texas, Oklahoma, Arkansas, and the Carolinas, such a pattern can create a winter defined by sharp contrasts, days of mild warmth interrupted suddenly by blasts of cold air or icy precipitation. Meanwhile, the northern branch of the jet stream was projected to carry warmer Pacific air across the Northwest, Montana, the Dakotas, and parts of the Great Lakes region. This northern flow could create pockets of warmth that linger longer than expected, reducing early season snow cover in some areas while generating brief periods of rain where snowfall is typical. NOAA scientists were careful to emphasize that a warm northern branch does not eliminate winter weather. Rather, shifts the distribution of snowfall and can lead to sudden transitions when the two branches interact. One of the most fascinating aspects of the 2025 jet stream split was how dynamic it appeared in NOAA simulations. Instead of locking into a static pattern, both branches showed signs of oscillation. They twisted, reconnected, and drifted apart again depending on pressure changes over the Pacific and Arctic. This oscillatory behavior meant that regions on either side of the winter divide could experience short but intense swings in temperature. A city might move from unseasonably warm weather to a sudden freeze in less than 48 hours. Those rapid temperature changes have far-reaching effects on agriculture, infrastructure, and energy demand. For meteorologists, such variability presents a challenge because it compresses multiple seasonal transitions into tight windows of time. The jet stream split also raised concerns about potential storm-blocking patterns. When the upper atmosphere divides, it occasionally creates stagnant pockets of high or low pressure that linger longer than usual. A high-pressure block can bring extended periods of dryness and stable temperatures, while a low-pressure block can trap moisture and cold air over a region, leading to extended stormy weather. NOAA's models indicated a heightened probability of blocking events over the western United States and the North Atlantic. These blocks could shape December's weather by forcing storms to take unusual paths, or by delaying their movement after formation. In quiet moments during NOAA's internal briefings, some scientists reflected on how this jet stream behavior might signal broader climatic change. The split appeared to be influenced by the same atmospheric and oceanic anomalies that were challenging long-held assumptions about winter timing and intensity. The atmosphere seemed to be redistributing energy differently, reorganizing the balance between cold Arctic air and warm subtropical air in ways that suggested a more fluid and less predictable winter pattern. For researchers accustomed to the jet stream's steady influence, watching it divide so distinctly was both scientifically fascinating and deeply humbling. As December 2025 approached, the idea of a winter divide became more than a theoretical model. It became a guiding framework for understanding how the United States might experience the coming month. Some areas could face enhanced storm activity, others could encounter unusual warmth, while many might move through a season shaped by contrasts rather than consistency. And through it all, the jet stream, that silent river of wind flowing high above the continent, would continue shifting, splitting, and guiding the atmosphere in ways most people would never see, but would certainly feel. In the changing winter air in the quiet corridors of NOAA's Climate Prediction Center, where long walls glow with shifting maps and data streams flicker like luminous threads, scientists spent the final weeks before December 2025 running scenario after scenario, studying how the unusual atmospheric patterns might translate into actual winter weather across the United States. It was not a single model that caught their attention, but the chorus of models, all hinting toward a winter where the atmosphere behaved less like a sequence of predictable steps and more like a series of sharp, unexpected pivots. Each simulation held its own story, its own version of December's unfolding, yet they all shared one defining theme: extremes knit tightly together, oscillating rapidly in ways that most winters rarely display. The first group of models focused on snowfall potential, especially in regions influenced by the newly split jet stream. In typical years, snowfall patterns follow a comfortable logic. Cold air settles in the north, storms track across familiar corridors, and snowfall accumulates gradually as winter deepens. But in the December 2025 simulations, NOAA saw corridors of intense snow that formed suddenly and shifted unexpectedly. Some models predicted atmospheric conditions capable of producing record snowfall in narrow bands stretching from the Central Plains into the Midwest. These bands emerged not because of a long, slow build-up, but because the southern branch of the jet stream was projected to carry dense waves of moisture into zones where cold Arctic air intermittently dropped south. It was the layering of these ingredients that intrigued scientists. Warm, moisture-rich air from the Pacific and Gulf of Mexico was expected to collide with colder continental air masses in rapid succession. When these air masses meet at just the right altitude and velocity, snow can develop with remarkable speed. These interactions produced simulations showing localized blizzards forming with little warning, leaving some regions buried under heavy snowfall, while neighboring areas remained relatively untouched. For meteorologists, this kind of sharply defined snow gradient is both challenging and scientifically captivating. A reminder that snow is not simply frozen water, but the result of an intricate alchemy between temperature, humidity, wind patterns, and atmospheric pressure. However, snowfall extremes were only part of the story. NOAA's thaw models painted a picture that contrasted sharply with the heavy snow scenarios. In several simulations, warm pulses surged through the northern branch of the jet stream, bringing temporary but pronounced warm-ups to areas accustomed to stable December cold. These warm surges were tied directly to the deep ocean warming pulse detected earlier in the Pacific. As heat radiated upward and outward, it influenced atmospheric ridges that allowed warm air to travel farther north than usual. Some models showed temperatures rising rapidly for 1 or 2 days before dropping again just as quickly. These short, intense warm periods had the potential to melt freshly fallen snow, saturate the ground, and then freeze again when cold air returned, creating layers of ice beneath subsequent snowfalls. Such rapid freeze-thaw cycles can shape an entire winter season. They influence river flows, increase the risk of ice accretion on roads and power lines, and create conditions where snowpack becomes denser and heavier over time. NOAA's hydrological models suggested that even regions expecting significant snowfall might face mid-month thaws that temporarily disrupt winter landscapes before cold air settles back in place. In some simulations, this warm-cold interplay repeated several times within a single month, an unusual rhythm that left scientists considering how the constant reshaping of snow and ice might affect everything from agriculture to transportation networks. Another scenario explored by NOAA involved coastal storm development. With the jet stream split and atmospheric moisture elevated, conditions were ripe for the formation of strong nor'easters along the eastern seaboard. In models where the southern jet strengthened, moisture pulled over the southeast before being drawn up the coast by a developing low-pressure system. When these systems formed offshore, they had the potential to gather strength quickly. Some simulations showed powerful storms developing just far enough from the coast to spare major cities from severe impacts, while others tracked the storms inland, delivering heavy precipitation and strong winds to urban corridors from Washington, D.C. to Boston. The interplay between cold continental air and warm Atlantic currents amplified the uncertainty around these coastal storms. Slight shifts in the jet stream trajectory altered storm intensities dramatically. If the cold air moved in earlier, snow dominated the precipitation. If warm air surged just a bit farther north, the same storm might bring heavy rain instead. As the pieces of NOAA's December 2025 projection come together, a clearer picture emerges, one painted not in sharp, alarming strokes, but in gentle, shifting layers that reveal how intricate and interconnected our planet truly is. The warm pulse rising from the Pacific, the hesitant breath of the Arctic, the wavering jet stream, the heavy moisture waiting in the atmosphere, the rapid freeze-thaw cycles, and the quiet adjustments in ecosystems and human systems alike all blend into a portrait of a world in motion. Not chaotic, not collapsing, but changing in ways that invite observation, curiosity, and understanding. Across the United States, December becomes more than a weather forecast. It becomes a reflection of the broader rhythms shaping the climate of the future. Families prepare for winter traditions beneath skies that behave differently from the winters they once knew. Communities along the coasts watch shifting storm tracks with the wisdom of experience. Farmers, travelers, workers, and students feel the quiet fingerprints of atmospheric change on their daily routines. And above them all, NOAA satellites, sensors, and models continue to trace the invisible currents guiding the winter ahead. What this moment ultimately offers is awareness, a recognition that Earth is always speaking, always signaling, always revealing the subtle ways its systems respond to heat, moisture, pressure, and time. December 2025 becomes a chapter in that vast planetary story, showing how the planet absorbs, adapts, and reshapes itself through the long arc of climate evolution. It reminds us that while weather may be experienced day by day, the deeper shifts unfold slowly, thoughtfully, almost meditatively, like the Earth, breathing in patterns too large for any one moment to define. And so the month arrives with a sense of quiet significance. A reminder that within every snowfall, every warm surge, every storm rolling in from the Pacific or spilling down from the Arctic, there are clues waiting to be understood. Clues that help us see how the planet is changing, how the seasons are evolving, and how we, as observers of this shared world, are learning to listen more closely to the science that guides us forward.